Hey guys. All right, so for this week, we're going to be looking at experiment 6, and this is going to be the moment of inertia lab. A pretty basic lab again. Basically, what we're going to be doing is just changing the shape of the beam that we are working with here, and we're going to be testing it and loading it under different increments and seeing how the stiffness changes just based off of the shape alone. So the material is going to be consistent throughout. And this video is just going to be by itself. Again, I've decided not to make another experimental video because it would only be like a minute long anyways. And we're still using the UTM, and we're using the aluminum beam that we've been using for the past like 4 labs now. So you guys should be pretty familiar with that, and you won't be missing much by seeing an experimental video. So let's get started. So again, the objectives is to analyze the effects of the geometric properties of a beam on the deflection. So mainly what we're going to be looking at is the relationship between the moment of inertia and the deflection of the beam, or the rate at which the beam deflects when it is loaded. So the rate at which it loads, or deflection, pretty much the slope of the loading and the deflection curve is called the stiffness of the beam. And that's really important because when we're in the linear elastic range, then we can use that as a predictive measurement to estimate if we load the beam, this X amount, how much would it actually bend, or how much would it deflect in the center. So if you've just like looked around, next time you're allowed to go in public and you see there's a lot of different types of shapes of beams. Of course, there's a lot of materials as well, but there's a lot of different shapes. And basically what these are trying to do are optimize the resistance to bending with the lowest weight. So we want to use the least amount of material as possible. And then we also want to use the lightest amount of material as possible, because then the overall structure is going to be lighter. And of course, this depends on the type of structure that you want. Like parking garages use these double T beams. Parking garages almost need to be heavy because the self-weight helps with this structural stiffness of them, as the cars are all, the dynamic loading from the cars and stuff. So they use these double T beams like here. But then depending on other situations, you can have different shapes, some weird funky looking shapes like this aluminum, and then of course our steel. So for this week, we're just going to look at 2 shapes, and we're keeping the material the same. And again, we're going to see how just changing the shape changes the moment, or changes the stiffness. So our materials and equipment are pretty straightforward. We're using the UTM. We're using that 1 foot long I-beam aluminum 6061 specimen. And then data acquisition systems and calipers. We're not using strain gauges on this one. We're using only the internal recording on the UTM. So you'll see in the measurements, I'm only giving you loading, and I'm only giving you deflection. And there's only like 4 or 5 data points anyways, but that's all we need. So when I say we're changing the shape, we're using the same beam, but what we're going to do is just tilt, or like rotate the beam 90 degrees to get a different shape. So generally what we've been doing is this I-beam shape, I shape. So I'm going to be calling this cross section I shape because it looks like an I, right? If we rotate this 90 degrees, we have what we're calling our H shape. So although the dimensions are the same, since the shape is at a different orientation and the beam is at a different orientation, the moment of inertia is going to be different. So that's going to be one of the steps. First is to calculate the moment of inertia when it's in its I orientation, and then also calculate the moment of inertia when it's in its H orientation. And again, the material is going to be the same. We're going to be loading it at the same rate. And we're going to be loading it to the same maximum load of 4,000 pounds. So we're going to see how the stiffness changes in this beam just by changing, the shape, just by rotating it 90 degrees. So for the lab report steps, first in the measurements, I'm giving you data for 2 trials. So that's going to be the loading for the I-beam shape, and then the loading for the H-beam shape. And also in your measurements, what I want you to do is calculate the moment of inertia for each shape, and use the dimensions on slide 3. So right here, these dimensions in the bottom right, you're going to use those dimensions. But what I want you to do is calculate the moment of inertia is using, calculated by hand. So hand is in quotation marks. You don't have to draw it by hand, but I do want to see the steps in your equation format. Don't just use a online like source. I know there's lots of online sources out there that you can just plug in the values for, or the dimensions for the I beam, and then it'll shoot out an IY and an IZ value. Please do it by hand. It's really basic because it's just 3 rectangles added together in the X format, and then in the Z format, it'll be a little bit more easier too. So you can use the online calculator to check your work, but make sure you show the equations actually step by step, how you can get the total moment of inertia when it's in its I shape and in its H shape. And then just use the units. It should be in inches to the fourth, because all the measurements that I gave you are in inches. And then also just recall, though, this is a big assumption here where we're assuming all of the beam cross sections are sharp, like rectangular shapes. If you look here, you can see that the flanges are kind of have a little curve to them, and they're not going to be exactly like rectangular. So this is going to be our idealized cross section. And there is going to be some source of error contributed to that. So make sure to discuss that like you should have been doing in the past couple labs. But this is what we're going to use still. We're going to assume that they're all rectangular shaped for the flanges in the web. All right, so the lab report steps, this is just following along in the instructions that I should also upload. So make sure you download that and review that as well. The first step, what you're going to do is plot on one graph the P, so that's the loading, versus the measured deflections, or the measured, the deflections in inches for each orientation. So on one graph, you're going to have the data from in the I coordinate system, or the I orientation and the H orientation. Make sure you distinguish between these two lines, or these two data points, because using Excel, it'll do that automatically. Just don't put them as one. And then using a trend line with the intercept at 0, 0, you're going to find the experimental beam stiffness for each beam orientation. So you're going to do that for I and H. So you'll have a K, or in this case, K is going to be our beam stiffness. So K experimental for I and H. And remember, the stiffness is just the slope of that trend line. So when we place the trend line at 0, 0, the intercept at 0, 0, it should be a linear trend line at number X. That's it. There's not going to be a plus B. There shouldn't be anything else in the equation. So that number before the X, the coefficient that you're multiplying the X by, is going to be your beam stiffness. And make sure you include the correct units in that, based off of whatever your P is, your loading, and your deflection. So then after that, you're going to find the theoretical stiffness for each orientation by calculating first the theoretical maximum deflection of a simply supported beam, and you'll see that equation in your instructions file. And then you're going to divide the max load value, so you'll see the maximum load in the data. You're going to divide that value by this calculated maximum deflection, or theoretical maximum deflection, and that will give you the theoretical stiffness, and that you'll just denote that as K theoretical. So then, of course, you're going to compare those two, the experimental and the theoretical. You're probably noticing a trend in all of these in all of these labs. That's pretty much what we're doing, is taking an experimental value and then comparing it to what the theory should be. And of course, you're going to ask yourself, are they the same? Are they close? And why would they not be the same? They're probably not going to be the same, because that's how all of these labs have been. We always will have some source of error in the beam that we're using, or in the equipment not being precise enough. So think about the sources of error and mention that in the discussion as well, but try to compare those two. I think this lab report has a little bit closer of experimental and theoretical values, because we aren't using those strain gauges that add a lot of error into it. And then, of course, the last step, maximum stress of the section. So that's going to be your sigma max. You'll see the equation in your instructions file. And then overall, based off of finding that sigma max for each beam orientation, which beam orientation, I or H, would you recommend using? So which one seems to be able to carry the most amount of stress? Remember, the weight is going to be the same in this case because it's the same beam. We're just rotating it 90 degrees. So in this case, whichever one is strongest, whichever one can carry the most internal stress, would most likely probably be the best beam orientation to use in your loading situation. So based off of all of this analysis, which one would you recommend using? You can just like put a little line and box it at the end there. So overall, the lab report summary, the drawings and figures, you're going to have the cross section of the beam orientation. So 2 cross sections, I and H, with all the dimensions, and then also show the profile view of the beam, like the simply supported with where we're loading it using the UTM. That like a example of that is on slide 3 of this PowerPoint. And then you're going to show the steps calculation steps for the moment of inertia for H and I. And then just like last week, the results, see the previous page and see your instruction file as well, but make sure to box all answers if you're not providing a final table of results, so I can just go through and see, okay, like this is the main answer, this is the main thing they're finding here. And that's it. So basic lab, I hope. I did tweak the data a little bit. It should be pretty accurate. Shouldn't have too much of a high source of error. So if you're calculating something like with a massive amount of error, then email me and I can look through it and see if it is correct or not. So good luck this week. I'm sorry I have been slacking on the grading. I'm going to get that done as soon as possible, and I will post that, and everything will be on web courses. Cool. Have a good one, guys. I'll talk to you again later.